Hello friends. So, in the previous lecture we have discussed regarding the requirement of linked net structure, and we have discussed that two algorithms are used in linked net structure, in which algorithm 1 is used to prepare the table which shows the various parameters like the next and far, and the algorithm 2 is used for the determination of primary backup relay pairs. And after that we have discussed one example on linked net structure, and in that we have considered one network which contains 4 branches and 8 relays, and we have discussed that if we consider this algorithm, then using the algorithm 1 of linked net structure, the whole table that is prepared, which is known as the branch network table, and that can be prepared for this network, and after preparation of that and utilizing that table, we can also go for the determination of primary backup relay pairs using algorithm 2 mentioned in the linked net structure. After that we have discussed that if we want to carry out the let us say we want to discuss or we want to find out the primary backup relay pairs for a large network which contains more number of branches and more relays, then we have to write some code, and for that we need some algorithm, and we have discussed that if we go for different IEEE larger bus network systems, then we can write down the code efficiently using these two algorithms and we can determine the primary backup relay pairs. So, till now what we have discussed is that coordination of protection in terms of 4 different aspects. The first is the coordination between two relays. So, OCR to OCR coordination, where OCR indicates the overcurrent relay. So, we have the coordination between overcurrent relays, that is one relay and the other relay. So, linked net structure indicates that if we have let us say 10 or 20 number of relays available in a particular network, then how the coordination among these relays that is to be carried out, and we have already discussed this is done by linked net structure. The second type of coordination is required in case of distribution network, that is between fuse and recloser. So, we know that fuse are widely used in distribution network. At transformer level also, let us say we have 11 kV by 415 volt transformer is there, where 11 kV is your 3 phase 3 wire system and your 415 volt is your 3 phase 4 wire system. There also we can use the DO or dropout fuses. At 415 volt level, we can use the fuses known as HRC, high rupturing capacity type of fuse. So, HRC fuse are very widely used 415 volt, and maybe at 230 volt also, that is our residential purpose or for domestic consumers, we can also go for the conventional KitKat type of fuse or maybe MCB also, because nowadays most of the domestic consumers they use MCB along with the ELCB. So, it is miniature circuit breaker or earth leakage circuit breaker. Sometimes it is also known as the RCCB, residual current circuit breakers. So, when our relay is connected, or recloser is also another device which is used at 11 kV substation, and these reclosers are we will discuss further also as we proceed in this lecture. So, the coordination among these different types and categories of fuses which we are using at different voltage level starting from 230 volt to 415 volt to 11 kV with recloser and relay, that is also required. So, that second type of fuse recloser coordination is very important as far as distribution network is concerned, and this also we will discuss here. Then coordination between two fuses, because we know that at 230 level we use fuse or MCB, and at 415 volt also we use let us say high rupturing capacity type of fuse. So, between two fuses coordination is also required. Nowadays most of the domestic consumers they use MCB, and even at 415 volt also instead of utilizing high rupturing capacity type of fuses, most of the utility they will also go for MCCB, that is molded case circuit breakers. So, coordination between two fuses, if we go for fuse, or coordination between MCB and MCCB, that is also very important when we talk about distribution network. And fourth, that is coordination between recloser and overcurrent relay, that is also required, but I think this is not that much important, because the overcurrent relay, whatever digital relay available, it has a feature inbuilt that it can also work as a recloser. So, I think this fourth option is not important, but second and third option is very important, and we will discuss further more about the second option. So, first option, that is coordination between overcurrent relays, we have discussed using linked net structure, and we have seen that if interconnected network is there where multiple sources are present, then how the coordination that is achieved. Now, before we go into second part, the first part which we have discussed, in that one more point is very important, is we know that nowadays the most of the utilities are encouraging the placement or interconnection of distributed energy resources. So, when we talk about the distributed energy resources, or we can call it as distributed generators, maybe in terms of solar, wind and some others, then this play also an important role. So, distribution system at present normally it is radial in nature, and hence normally whatever is the power flow, that is unidirectional in nature from substation to the load, or maybe from right hand side to left hand side, or maybe left hand side to right hand side, whatever it is. Due to incorporation of these distributed generators or distributed energy resources, this are in terms of solar PV or wind or any other like fuel cell or so on. So, alternate current path exist, and whatever distribution network or structure, radial structure is there, that may lost. So, now our conventional distribution network, that does not remain radial in nature. So, when we incorporate the distributed generators in terms of solar PV, wind, then distribution system imposes barriers in terms of we observed miscoordination among various protective devices if proper care that is not taken. Sometimes it is also observed that the reach of overcurrent relay also reduces, and sometimes it is also observed that sympathetic tripping is also there. Sympathetic tripping means it is nothing but a phenomena where if fault occurs in one particular section and the relay located in other section operates, then those operation of relays, that is known as sympathetic tripping. So, these three phenomena are the impact of incorporation of distributed generators when we talk about the coordination among the relays using linked net structure. Now, when we talk about the coordination of relay and we know that the relay may maloperate, which we called as miscoordination among various relays. This is increased when the location of DG changes, when the capacity of DG changes, and when the number of DGs connected in the distribution network, that also changes. So, more number of DGs are connected into the network, the miscoordination among relays that is observed. Even when we consider the impact of fault resistance, then this problem becomes more compounded. So, the overall impact when we talk about incorporation of DG in the distribution network with reference to the coordination among overcurrent relays, then the main two impacts are delayed operation, or sometimes in worst case relay may not operate, and failure of our conventional relays, that is also observed. So, let us understand this thing, how the relay miscoordinate when we incorporate distributed generators in a radial distribution network with some example. So, here let us consider this system in which the three sections are shown, section 1, section 2 and section 3, and these three feeders are connected between the 4 buses, bus A, bus B, bus C and bus D. We have a source connected near bus A, and the loads are connected at each bus starting from D, C, B and so on, and at present only 3 relays are connected, let us say at R1, R2 and R3, all 3 relays are bidirectional in nature. You can also consider directional relays also, and at present no such DG is connected with this radial distribution network. So, when we talk about the fault in this third section, CD section, then obviously whenever fault occurs at bus C, the fault current is maximum compared to the occurrence of fault at bus D, right. So, when we talk about the section CD, then what we want is that the time of operation of relay R2 should be greater than the time of operation of relay R3 by some margin, and that margin we can call it as minimum discriminative time, or sometimes it is also known as coordination time interval CTI. So, the meaning is that if fault occurs in this section, let us say at F3, then relay R3 must operate as a primary relay. So, R3 has to operate first. If R3 fails to operate, then R2 has to provide backup. Similarly, so on, if fault occurs in section 2 at F2, then R2 must operate first, and if R2 fails because of some reason, then R1 will provide backup. So, if we understand this by plotting the characteristic of R3, R2 and R1 relays, because all 3 are inverse definite minimum time relays. So, if we talk in terms of the characteristic of these 3 relays, then we can plot the characteristic of 3 relays considering on x axis the multiple of pickup currents. So, this is nothing but the multiple of pickup currents or MP is nothing but fault current referred to CT secondary divided by relay pickup current or plug setting of the relay. And if I consider the time in second on y axis, then we can plot the characteristic of relay R3, relay R2 and relay R1 like this, right. I have shown R1, R2 and R3 relay characteristic by different 3 colors, and you can see that characteristic of R3 comes first, because we want that relay R3 should operate first because it is connected near to the load, and as we progressively move towards the source, the further the R2 characteristic comes and then R1 characteristic comes. Now, we are talking about the minimum discrimination time between 2 relays, let us say R2 and R3. So, you can see that this is the point and this is the point. So, these 2 points are decided by considering the maximum fault current at bus C. So, if I consider maximum fault current at this bus and maximum fault current at this bus at bus C and bus D, then I have seen here the maximum fault current at bus C and maybe maximum fault current at bus B or bus D, whatever you consider. So, based on that you can plot the characteristic and you can see that this much margin is available between R2 and R3, this is the margin, and between R2 and R1 this is the margin available, and this margin is known as the minimum discrimination time. So, this margin between the characteristic of 2 relays depends on errors available in the relay. So, let us say for example, how the errors in relay changes the value of MDT. So, it may possible that my relay R3 which is following this blue curve, it may possible that this relay will operate with slight delayed, right. So, you can see that this characteristic of relay R3 which is shown in blue color, that is shifted slightly upward. So, then obviously you can see this margin which is MDT, that is going to reduce. So, errors in relay means your whatever relay which is prescribed for particular operation, relay may operate earlier or it may operate slightly slower also, and same is the situation for relay R2 and for relay R3. Similarly, errors in circuit breaker is also there, because relay once operates, senses the fault, it gives signal to the breaker. So, there has to be some time delay in the operation of circuit breaker. As the circuit breaker installed and as the time progresses, then obviously the breaker operation that is also affected. And the third thing is the ratio and phase angle error in the CT and PT, that is also is another factor which is going to affect the value of MDT. And why we are stressing more on MDT? Because minimum discrimination time is the some margin available between two relays. If this margin is not available, then for a particular fault maybe two relays or more than two relays may operate simultaneously, which is against this selectivity criteria of the protective system. So, that is why this margin is very important. Now, this margin is okay when we do not connect any DG in the radial distribution network, then we have this sufficient margin. Now, let us consider same radial network, but we have connected or we have incorporated distributed generators or distributed energy resources, maybe in terms of solar, wind and so on at different buses. So, when we connect the DG, let us consider different possibilities. So, first possibilities I am taking that two DGs, DG1 and DG2 are connected at bus B and bus C respectively as shown in the figure. So, if this is the case, then we know that if I consider now this third section, that is section connected between C and D, and if fault occurs in this section somewhere here at F3, then the current that flows through relay R3, what is the current that flows through relay R3? So, that current is the current from the utility I utility plus the current that is available from or fed by this DG1. So, I DG1 it is also there plus the current fed by this I DG2. So, this is the addition of all these three currents that will flow through relay R3, whereas from relay R2 the currents that flows, that is the I utility plus I DG1. So, now you can see that in earlier case when no DGs are connected, the current flows through the relay R1, R2, R3 are same, whereas when we connect the DG at two buses, let us say B and C, the current that flows through the relay R3 and relay R2 changes. And obviously, this currents which flows through relay R3 and R2 that increases because of the additional fault current fed by these two DGs, DG1 and DG2. So, these two relays R3 and R2 need to be coordinated at larger magnitude of fault current. So, this is very important. Now, on the other hand, if I consider let us say the fault in section 1, let us say F1, the first case we have considered where we consider the fault at F3 in section 3. Now, here I am considering fault at F1 in section 1, right, between AB. So, here now you can see that when fault occurs in section AB, then the current flows through relay R2, that is again fed by this DG2 only, whereas from relay R3 no current flows because no DG is connected. So, now when the reverse flow is there, right. So, whenever fault occurs at F3, this faults because it is near the load, we can call it as downstream fault, and whenever any fault occurs let us say at F1 which is near the source, we can call it as upstream fault. So, this is very important where we consider the two DGs, then the current flows through the relay increase because of additional fed of the current by the DGs, and these two relays are coordinated at larger magnitude of fault current, and even current flows through R3 and R2, that is also entirely different. Now, let us consider the another possibility too, in which I have connected only DG3 at bus D. So, when this is the case, you can see that both relay R2 and R3 will sense same current for any upstream or downstream fault. So, if fault occurs let us say at downstream side here, then the current flows through relay R2 and R3, that is only from the utility side. So, utility will feed the current, and if fault occurs let us say somewhere here at the upstream side at F1, then also you can see the current fed by this DG, that will again like this. So, current flows through the R2 and R3, that will remain same, it is fed by DG3 only. So, what we want now? So, in this case we want that relay R3 should operate before relay R2 for any fault in section CD. So, any downstream fault somewhere here between section CD at F3, we want that R3 must operate before R2. But what we want on the other side, if there is a fault on upstream side at say in section 1 at F1, then we want the reverse operation. We want that R2 must operate and R3 should operate after that. Now, let us consider the third possibility where all the DGs are connected. So, DG1 is connected at bus B, DG2 is connected at substation C and DG3 is connected at substation D. So, now in this case for any fault in section CD, let us say this is our section 3, section 2 and section 1. Any downstream fault in section CD, because we are discussing for this third possibility where all DGs are connected, let us consider first that fault occurs on the downstream side. So, at F3 in section 3. So, for a fault in section CD, R3 will sense maximum fault current followed by the current sensed by R2 and then current sensed by R1. So, maximum fault current will depend on size of the DG, type of the DG and placement of the DG in a particular section, right. So, if I consider let us say fault at F3 here in section 3, this is known as downstream fault. Then in this case obviously the current that is sensed by relay R3 is again the same as I told you, it is IU plus IDG1 plus IDG2, and whereas the current through R2 that is only IU plus IDG1, right. So, again there is a difference in the current flows through the relay R3 and relay R2 for any downstream fault, let us say at section 3 at F3. So, again let us consider the same third section here, this is our section 2. So, this is my section 1. Now, let us say we are coordinating relay R3 with relay R2 and we are coordinating relay R2 with relay R1, and the fault is going to occur in section CD, let us say at F3. So, in this case for this fault, as R2 senses less current than R3, why? Because through R3 the current that flows is IU plus IDG1 plus IDG2, whereas from R2 current flows that is IU plus IDG1. So, as R2 senses the less current than the R3, so the R2 curve has to shift down, and you can see that I have shown the characteristic of R1 with this color, R2 with black color and R3 with this original blue color. Now, the characteristic of R2 has to shift below. So, you can see I have mentioned here R2 revised. So, which is shown by dotted black color. So, now you can see in earlier case between R2 and R3 this much margin is available, right, but now because of shifting of this characteristic curve of R2, the margin available that is going to be reduced, and that depends on placement of DG, type of DG and the capacity of DG. So, this is very important. Similarly, when we coordinate relay R2 with relay R1, then also for a fault in another section, let us say in this case also curve of R1 will shift, and again my minimum discrimination time which is available between R2 and R1 is like this, which is going to reduce from this to this. So, this is very important point as far as the margin between two relays is concerned, and this margin is going to reduce when we connect the more number of DGs at different location and with different capacity. Now, let us consider the third possibility where all the DGs are connected, that is DG1, DG2 and DG3 are connected at bus B, C and D, and the fault we are considering, that is the upstream fault, means those faults which are going to occur near the source. So, let us say we have this is our section 1, this is our section 2 and let us say this is our section 3, and fault that is going to occur let us say at F1 in section 1. So, this is nothing but the upstream fault. in this fault at F1, relay R2 will sense more fault than the relay R3. So, obviously, when fault occurs at F1, one of the flow of the current from the utility side is like this, and the second side, if you consider the relay R2 and R3, then relay R3 the current flows that is only by IDG3, and through relay R2 the current flows that is because of IDG2 plus IDG3. So, more current will flow from R2 than relay R3 for a fault at F1. So, in this case what we want is that obviously as more current will flow from relay R2. So, R2 should operate first, then relay R3 will operate, and because of this obviously the margin between the two relays that is going to reduce, as I told you. When this difference of this margin, right, that is MDT, and difference of these two fault currents, let us say IF R2 and IF R3. So, when difference of these two fault currents is less than the minimum discrimination time margin. So, this margin is let us say reduced because of placement of DG, and when this value, this difference is less than MDT, then miscoordination of relays will be definitely there, and we cannot avoid that. And for that we need to use some other philosophy or algorithm if we wish to avoid miscoordination among different overcurrent relays. So, what we have discussed in this class is that initially we started our discussion with the 4 categories or 4 possibilities, that is the coordination between two relays, OCR to OCR, overcurrent relays to overcurrent relays. Second, we have considered the coordination between fuse and recloser. Third, we have considered the coordination between fuse and fuse, or maybe MCB and MCCB, and fourth we are considering coordination between the overcurrent relay and the recloser. And then we have discussed that the fourth possibility is very important. So, the first possibility, when we consider the overcurrent relay coordination with other overcurrent relays available in the network, then when we connect or when we penetrate more number of DGs, that is renewable energy sources, into the radial distribution network, then the radial structure of the distribution network is lost and it becomes multi source system, and in that case minimum discrimination time between the two relay characteristic, that is very important. And when the difference in fault current between two adjacent relays, if that is lower than the minimum discrimination time between the two consecutive relays or adjacent relays, then the miscoordination or the coordination between two relays, that is lost, and that is very important, because when we connect more number of DGs into the network, then depending upon the location, capacity and size of the DGs, the current flows through the relay that is different when we consider the downstream fault compared to when we consider the upstream fault in the network. So, this is very important as far as the coordination between two relays are concerned. So, in the next class we will discuss more about the coordination between fuse and reclosers. Thank you.